family happy on Tsinghua campus. So we are developing very well everywhere, in Tsinghua, in Shanghai, and in Shenzhen. So you are all welcome to come here for joining us. We will make sure to make you happy and peaceful and doing good research. Anyway, today we have the talk by Becker, whose title is Degree of Maps and Applications. Okay, Coach.
Hello, good morning. Thank you, Professor Yao, for the kind introduction, and thanks the organizers for the invitation to give a talk here. So today I'm going to talk about a new direction of research in algebraic geometry, and I'm going to stick to very simple terminology and settings. I won't try to get into too much technicalities, except maybe at the end of the talk. So this topic, I think, is the notion I'm going to introduce is very basic, and so it should appear, I think, in many different places in algebraic geometry in some form, and it has the potential to grow into a whole new direction. Let's start with some very simple elementary algebra. We all know field extensions is quite important in algebra, number theory, and algebraic geometry. If we have a field extension K to L, then one of the basic invariants to associate to this field extension is the degree. You simply take the dimension of the larger field as a vector space over the smaller field. Of course, this can be finite, it can be also infinite. So let's just remind you of some very basic examples. If we take the field of rational numbers and add the square root of 2, then we get a larger field, and the degree of this larger field over Q is simply 2. We can calculate the degree of these fields by looking at essentially the polynomial associated to this new element. A similar example is if you add the third root of 2, then you get again a larger field, and this time you will need 3 elements to generate this bigger field, and so the degree becomes 3. For finite fields, if you start with Fp, the finite field with p elements, then this sits inside a larger finite field, Fp to the n, and this extension has degree n. On the other hand, the field of complex numbers or real numbers over the rationals, we know that this has infinite degree. So these are very simple examples of field extensions. Okay, but I'm going to do algebraic geometry today, so we can generalize this to the setting of algebraic varieties. And for this, we look at finite morphisms between 2 algebraic varieties. If we take a morphism x to y between algebraic varieties, we say that this is finite basically if locally you have, so locally you can take an affine open subset. This is similar to an open, like a disk in a manifold. And you look at the inverse image, we require the inverse image to be affine also. This means it should be given by a ring. And then you have a corresponding ring extension. You can also define degree similar to field extensions. And we want these to be finite. So in other words, the larger field should be a finitely generated module over the smaller ring. Okay, so once you have a finite morphism, you can define the degree. The degree is given by the degree of the corresponding function fields. Function fields means the field of all the rational maps on algebraic variety. This corresponds to like the field of meromorphic functions on manifolds. So you can define the degree, and this is finite because the morphism is finite. If the morphism is not finite, you can have infinite degree, but here we have finite. So this generalizes basically the field extensions to the setting of algebraic varieties, where we consider finite morphisms. And the degree is, again, a very basic invariant. So you can also see this more geometrically. If we, in particular, work over algebraically closed fields, let's say if you work over the complex numbers, then this degree essentially is, if you pick a general point and look at the inverse image, then you will have exactly degree distinct points. So you can see this also in terms of geometry. Okay, so let's look at some, again, very basic examples for the students. If we take the affine line A1 to A1, so if you work over the complex numbers, this is just complex numbers to complex numbers, and you take an element t to t squared, then you can calculate the degree of this finite map is simply is the degree of the field generated by one variable here over the field generated by t squared. And you can calculate that the degree is actually 2. And this is not surprising, because if you look at here, if you pick an element in the second A1, then the inverse image generally will have exactly 2 points, which corresponds to this degree being 2. A similar example is given by a polynomial of degree 3, and you can guess immediately what the degree should be. It should be 3, because the polynomial has degree 3. Inverse image of elements will have 3 distinct points, and therefore the degree is 3. Okay, so let's just give a couple of more examples for the students. This time I'm taking a less obvious morphism from A1. A1, again, is just like taking the ground field, like the complex numbers. This time I'm defining this map to the subset of the two-dimensional affine space defined by this polynomial, y squared minus x to the 3. This gives you a one-dimensional algebraic variety, which is singular, so it doesn't look like a manifold anymore. But still, we can calculate the degree of this map. In fact, this map is finite, and the degree happens to be exactly 1, which is not surprising because it turns out to be a birational map. This is, in fact, this map is simply resolving the singularity of this algebraic curve. And therefore, not surprisingly, the degree is exactly 1. For general points, the inverse image is precisely just 1 point. Another example is to, again, work inside the two-dimensional affine space and take these polynomials, this degree 3 polynomial, which gives you now a degree, so this defines a degree 3 algebraic curve. And I'm going to define the map from this algebraic variety to A1 simply by projection. Then again, we can calculate the degree in terms of fields and so on, or just in terms of inverse image of points, and we can see that the degree in this case is exactly 2. So this is not surprising. This simply says that if you fix x, a number, a general number, then you solve this equation y squared is equal to something, and that has exactly 2 solutions, so the degree must be 2. Okay, and similarly, we have this map from AN to AN defined by powers of 5 of all the variables here, and then this time you can calculate the degrees 5 to the number of the variables that you have. So if you raise to the power 7, then you have 7 to the n. Okay, so these are very elementary examples of finite morphisms between algebraic varieties and the calculation of their degrees. Okay, so I'm going to try to generalize this concept to non-finite morphisms. So now consider proper morphism of algebraic varieties. if you are familiar with the terminology, consider a much more general setting of Noetherian schemes. But if you are not comfortable with these things, just think about algebraic varieties. Okay, so suppose that this is a proper or like a projective morphism, then a very basic fact in algebraic geometry says that you can decompose this map into two parts. One part, the second part, is a finite morphism. But the first part is a completely different kind of map. It's like more or less the opposite of finite, in the sense that its fibers are all connected. So if you take any fiber and look at the topology of this fiber, it's connected. It doesn't have like two different connected components. More technically, the first map is a proper map, again, with connected fibers, and in particular, its structure sheaf is given simply by the push forward of the structure sheaf of X. But the second part is finite, as I said. Okay, so this is called the Stein factorization of a proper map. Okay, so let's consider a very simple example of this kind of maps. Let's take X to be the algebraic variety inside P squared times A1. P squared is the two-dimensional projective space defined by this polynomial, which has degree 2 in the variables on the projective space, and it has degree 1 in the variable over the affine line. We define the map from X to the base to A1 simply by taking a point X, Y, Z, T to T squared. So essentially just forget about X, Y, Z and takes the T to T squared. Then we can see that over non-zero numbers, the fiber has exactly 2 connected components. And therefore, if we look at the Stein factorization, then it should give us something non-trivial. And in fact, it does. This map decomposes into 2 parts. The first part is simply projection. It takes this point to T instead of T squared. And the second part will just take T to T squared. So it just decomposes into this part where fibers are connected. Second part, the fibers are not connected. They have 2 connected components. Okay, so these are all very elementary algebraic geometry. And I'm going to use this Stein factorization to define the Stein degree, which generalizes the degree of field extensions and degree of finite morphisms to proper morphisms of algebraic varieties, and you can also consider more generally schemes. So let's say for now, for simplicity, let's just look at algebraic varieties. Suppose we have a morphism X to Y of varieties defined over some field. It can be algebraically closed or not algebraically closed. We will see later that this is quite interesting also from an arithmetic point of view. And then we define, so we take the Stein factorization of this map. Remember, the second part is a finite map. And then we define the Stein degree of this map F, or simply write X over Y, to be the degree of the finite part of the Stein factorization, if the map is surjective. But if it is not, we just put this to be 0. Okay, so Stein degree, remember, is just the degree of the finite part. Equivalently, the Stein degree in the surjective case is just the number of connected components of the fibers, of general fibers. This notion was first formally introduced in one of my papers on moduli theory. I was trying to construct moduli, compact moduli of algebraic varieties, and then at some point I realized that I need this kind of degrees in order to understand how different components of a scheme glue together. And this is controlled by this Stein degree. And now suppose that we look at, we pick a point inside X, and we look at the image inside Y. I'm here assuming that the point I take in X is a closed point. So if you work over algebraically closed fields, so this essentially means any point. But if you work over non-closed fields, then that becomes more interesting. So you can take any closed point, the image is also a closed point, and then you can define or look at the Stein degree of the point little x over the little y. So I'm not looking at the Stein degree of the whole space over the base. I'm just looking at a different Stein degree. Then this Stein degree is precisely the arithmetic degree, or in other words, the degree of the residue field of x over the residue field of y. And this is a very basic and important invariant in arithmetic geometry. It essentially measures how complicated or how far the arithmetic of these 2 points are from each other. Okay, let's look at some examples. If you have a birational map, proper birational map, then not surprisingly, the Stein degree will be 1, because birational maps are isomorphisms over some open set. Generically, they are isomorphisms, and therefore, you have connected fibers, general fibers, and the Stein degree is exactly 1, so that is not surprising. Let's look at a few more elementary examples, and then afterwards I will look at more non-trivial facts about this Stein degree. Although the definition is very basic, but in fact the results that I'm going to tell you later are quite non-trivial, and they also rely on very non-trivial machinery. So you can get quite complicated stuff out of this Stein degree. But first, let's look at some basic examples just to have a good sense of what the Stein degree is. Let's look at this map from P1 to P1, which sends xy to x squared, y squared. This is, in fact, a finite morphism. And if we look at the Stein factorization of this, then because the map is finite, the first part of the Stein factorization is just the identity, and the second part is just the same map itself. This is just the finite part, which is the same as f. And then we can calculate the degree of this. The Stein degree is just the degree of the finite map, which is exactly 2. Another example, kind of similar to one of the examples that I described before, is taking this, again, the variety given by this polynomial equation inside p squared times a1, and I'm going to send the point x, y, z, t to t to the n for any fixed number n. Then we can see that the fibers of x to y, unless n is equal to 1, the fibers, general fibers, are not connected. They have different connected components, and therefore you should get something non-trivial here. And in fact, if we do the Stein factorization, then we see that the finite map has exactly degree n, and therefore the Stein degree of x over y becomes precisely n. Okay, so why do we care about this Stein degree? As I mentioned, one of the places that it plays a key role is in moduli theory. In moduli theory, when you try to compactify moduli spaces, even if you look at moduli of, let's say, manifolds of smooth projective varieties, then the limits, the degenerations usually have more than one component. Almost always the degeneration is quite complicated. So you have to understand how these different components glue together to make the whole space. And that's where the Stein degree comes into the picture. But it also actually plays a key role in understanding some of the key invariants in birational geometry. In particular, when you have a birational map, or sometimes you just have rational maps, you want to understand, for example, what subspaces are contracted. To understand the complexity of this kind of maps, this time degree naturally comes into the picture. But as I say, to prove something about them is actually very non-trivial. More recently also, again, related to birational geometry, some people also have used the sign degree in the context of motivic invariance of birational maps. Okay, so this is just a list of a few topics, but I'm pretty confident this will grow into a lot more. In particular, from a number theoretic and arithmetic point of view, there will be also applications of this time degree. But today I'm going to just essentially stay mostly in the setting of birational geometry and consider the following question. Under what kind of condition we can control this time degree, or more precisely, put a bound on it? If you look at these examples, for example, this one here, the previous example, the sign degree here is n, so n can be any number. And even this map is pretty simple, but this time degree can be anything. So if you want to have a control of these numbers, then you need to impose some conditions on the map and on the spaces. And this condition turns out to be related to positivity or lack of positivity. So in some sense is related to curvature of spaces or maps. And the relationship is quite also interesting. Okay, but in order to say something interesting, I need to discuss singularities and also pairs in the context of birational geometry. But again, I'm going to stick to very simple settings so that it will be more understandable. So in the world of birational geometry, we usually look at not only of one single space, but rather several spaces together. In particular, pairs, where you consider an ambient space together with some closed subsets, which we usually take to be divisors, but actually even that is not necessary. You could simply take a closed subscheme. It can be quite complicated, but usually you can reduce problems to this setting. So I'm going then to discuss this more standard setting of pairs. So what is a pair? A pair is you take xb, this is a normal algebraic variety x, together with a boundary divisor b. This is just a finite linear combination of codimension 1 closed subsets, or in other words, prime divisors. So if you work in dimension 1, let's say if x is a smooth curve, then a boundary essentially is just picking finitely many points and assigning a number to each of these points. That is a boundary divisor. Or more classically, if you take a non-compact algebraic variety, you can compactify it, and the compactification you can do in a way that what you add is, it has codimension 1, and that is in fact where the word boundary comes from. When you have something open and you compactify, what you add is just a boundary. But this is a more general definition, and also you have coefficients here. You don't just take coefficient 1, but you have rational, or even you can allow real coefficients. So this turns this machinery of pairs into a very powerful machine in algebraic geometry that you can do a lot of things. And in the last 40, 50 years, this has been used to really prove, to go to the extreme, like go to prove really highly non-trivial facts, relying on this machinery. Okay, for today's talk, I'm going to talk to just introduce two types of singularities in a kind of formal way, although later I will show you some examples. But for now, you can just think of it as some way of measuring singularities. Okay, so what you do, in order to measure how complicated a singularity is, there are a few techniques to do that. Sometimes people deform, or sometimes people use more topological techniques like Milnor fibers and numbers and so on. But I think the most powerful way of measuring a singularity is by taking a resolution of the singularity and just see what happens in the process. That gives you the most control over the singularity and to measure it, how complicated it is. So we measure, so we take a resolution of the singularities of X together with everything that is involved, all the divisor, whatever is there, we resolve all the singularities at the same time. So in characteristic 0, we know that we can do this thanks to Hironaka. Also in positive characteristic, this is still not a settled problem. Okay, so we do this resolution and then we pull back our data, which is here kx means the canonical bundle, canonical divisor, plus our extra structure, the boundary. We pull it back. We can write it in the same form, canonical divisor plus an extra, like a boundary divisor. And then we look at the coefficients of this divisor. That coefficient tell us how complicated the singularity is. In fact, the larger the multiplicities or the coefficients, the deeper the singularity should be. And I'm going just to formally say that if all the coefficients are strictly less than 1, we have KLT or Kawamata log terminal singularities. If you have coefficients less than or equal to 1, you have log canonical or LC. Of course, the difference is like a very tiny thing, but in reality, there is a huge gap between these two categories of singularities. Of course, if the singularities are too complicated, then the coefficients can jump over 1, but somehow everything breaks down. There are exceptions, of course. There are some statements where it applies to deeper singularities, but somehow almost every fundamental result in algebraic geometry fails if you go beyond 1. So this is maybe some kind of a mystery why this happens. So that's why we stick to coefficients at most 1. And given a pair xb, we can look at the deepest part of the singularities on this space. What we do, we just look at all the points where the pair is not KLT. Or equivalently, we can look at the resolution and take all the components in BW that have coefficient 1 or higher. We just take their union and push it down. We call that the non-KLT locus. So the terminology is quite obvious. It's just where you don't have KLT singularities. That is like the deepest part of the singularities. And that's also where usually the most mysterious part of the space is. Okay, so I'm going to give you some very basic examples first of pairs, just to get a sense of what they are and what we are about to talk here. So let's start with the simplest case of a smooth curve. So this is just a one-dimensional because we are assuming the space to be normal in dimension 1, so automatically it has to be smooth. Okay, and of course, if you work in over non-closed fields, more complicated things can happen. But let's pretend we work over the complex numbers. Okay, now let's take our boundary B to be half of a point plus another point. These are two distinct points. Okay, so let's see what kind of singularities we have. Well, because the space, everything is smooth here, you don't need to take any resolution. Resolution is just is arbitrary, it's an isomorphism. So you can measure the singularities already just by looking at the coefficients. Well, we have a coefficient is half, another one is 1. We don't have anything more than 1. Therefore, we are in the low canonical LC category of singularities. And the non-KLT locus is precisely this point, P2. So instead of 1 here, if we had like 5 times P2, then the singularity will not be LC, but the non-KLT locus still would be the same point, P2. So in dimension 1, this is just really very straightforward. And in a higher dimension, if the space is already smooth, the divisor or smooth and normal crossing, then again, you can measure singularities directly without doing basically any geometry, just combinatorics. Okay, so let's look at a slightly less obvious example. This time I'm taking x to be P2 and take L1, L2, L3 to be 3 different lines but passing through a point P. The coefficients here I'm taking to be 2/3 for each component. Then we can try to see what kind of singularities we have. We need to resolve the singularities. That precisely means blowing up that intersection point. If you do that, you already resolve all the singularities because it's a very simple setting. And then you get one exceptional divisor, E. You can calculate the coefficient of E in this BW, and you can see that that is precisely 1. And therefore, our pair has LC singularities, and its deepest part of singularities is precisely this intersection point P. If you take different coefficients, then you can do the same thing and do all the calculations. You can do it because the resolution process is extremely simple. However, even inside P2, if you take, instead of lines, if you take higher degree complicated curves, in fact, the resolution can be very non-trivial, even in this two-dimensional example. But in theory, if you are given any example, you should be able to do the calculations and determine what kind of singularities you have. Okay, sticking with the same space, P2, I could take my boundary to be 2 times a line, a double line. This time, my pair is not KLT because some coefficient is more than 1, and its non-KLT locus is precisely that line. Outside the line, everything is even smooth and nice, but it's only along that line that you have bad singularities. Okay, so these are very basic and elementary examples, but we can, just for the sake of completeness, look at more complicated examples. If you take x to be the cone over a rational curve, then it's well known that you get KLT singularities. But if you change the rational curve to an elliptic curve, the cone over an elliptic curve is not KLT anymore, it is low canonical. So this is, again, is a basic, more or less elementary example, but it already contains a really fundamental, not result, but hint in algebraic geometry, which is that this KLT category somehow corresponds to the global notion of a Fano variety. There is a very fundamental connection, although highly non-trivial, between Fano varieties, these are global objects, and KLT singularities, which are local objects. But on the other hand, when you go to LC, that connection is more related to Calabi-Yau varieties, not Fano varieties. So again, there is a quite non-trivial fundamental connection between these global Calabi-Yau objects and these local low canonical singularities. Okay, and if you take a quotient singularity, so that means taking the quotient of a smooth variety by a finite group, then you always get KLT singularities. If you look at the toric world, if your X is a toric variety, your boundary, all the components are toric, torus are invariant, then you always get low canonical singularities. It can be KLT depending on the coefficients. If you allow some coefficient to be 1, then you just get low canonical. And if you take surface dual singularities, these are KLT, but it's not surprising because these are all quotient singularities. So these are a bit more non-trivial examples. Of course, you can write down a much more complicated list. In my career as a student and as a mathematician, I think I have never seen anything more fascinating than the notion of singularity. It somehow contains almost everything in mathematics. In fact, if you take any projective variety and just take the cone over that variety, then that cone, which is just a singularity. It contains all the information, the global information about your projective variety. So that means that global geometry is simply a subset of the theory of singularities. But singularities can say a lot more about geometry than just global geometry. So anyway, we don't have too much time, I guess, so let me leave the basics and say a few more, maybe less familiar topics and results. Okay, so let's start with this so-called connectedness principle. This is something that people realized about 40 years ago in the work of Shokurov and later generalized to higher dimension by Kolar. It basically says something like this. Suppose that you have a pair, XB, and together with a proper map with connected fibers. So this XY itself, it has trivial Stein factorization. So its Stein degree is 1. We are not trying to measure the Stein degree of this map, but rather of subspaces. Okay, but assume that minus k plus b is ample over the base. So this essentially means you are in the Fano category, but in the sense of pairs. So you put some assumptions on the positivity or on the curvature, basically. Then this result, this very interesting result, is say that if you look at the non-Kelty, so the deepest part of the singularity, then it always has connected fibers over the base. So as I said, x to y itself, we are not trying to measure the Stein degree of that, but rather of some subspace where the singularities are bad or the deepest. And these results say that, in fact, you cannot have disconnected fibers. That's a really very interesting fact. And it also has many important applications in algebraic geometry. So this essentially says that if you take the non-Kelty locus of this pair, then over the base, the Stein degree is 1. Of course, you can have many different components, so you need to be a little bit careful about here. These are not just varieties. They have several different components. But this essentially just says the Stein degree in this setting is exactly 1. Okay, so as I say, this has many interesting applications, but I'm going to skip talking about the applications. Instead, let me just give you one, going back to one of the examples we considered before, where we had P2 together with this boundary divisor, 2/3 of 3 lines passing through a point. Then we can do some simple calculations. We can see that minus k plus b is, in fact, ample over the base. Over our base. The base, remember, was this. We just had projection onto. The base is just a point. Okay, and in this case, we can see that the non-Kelty locus is exactly 1 point, and it is connected, of course. But this result, but the example is obviously kind of trivial. But the results tell you that if you impose this condition on the positivity of minus k plus b, you cannot create 2 different isolated points in that singularity. You can at most get 1 point, and that is quite interesting. But if you remove that assumption on the positivity, then you can get any number of points. You can get arbitrary number of bad singularities. You simply take your boundary to be given by some high degree curves, and then there will be lots of intersection points. You can create many different singularities. Okay, so I think I should have put some coefficients here. Otherwise, the non-Kelty locus will be the union of the curves. But we can arrange things so that we have arbitrary number of points. So that means that this positivity of minus k is quite important. When you leave that, then everything can break down. Okay, so let me then try to state the main result that I was thinking about to state. For that, I need to introduce the notion of local labial vibration. This is it's a more general form of Fano vibration. So it includes Fanos, it includes calabials, it includes many things in between. So I'm just calling it a local labial, or LCYF. This means you have a pair XB over a base Y, and you have the calabial condition in the sense that K plus B is numerically trivial over the base. So if you just have X usual calabial manifold and Y is a point, then that would be one example. But here we are allowing vibrations, we are allowing boundary divisors, so you get a huge range of possibilities, including, as I said, all the Fano vibrations. Okay, so in that work on moduli, one of the things I proved that was that if you look at such a local labial vibration, and if you look at any component of the boundary with coefficient 1, which is horizontal over the base, then the Stein degree will be universally bounded only depending on the dimension. And that was a kind of quite surprising fact, that you put a really very minimal set of assumptions, but still you get this universal bound on the Stein degree. So that just is saying that if you look at the number of connected fibers of S over the base, it cannot be too large. It has to be universally bounded only in terms of the dimension. And that was kind of quite surprising. Okay, so let's just look at a basic example of a very basic example where I take X to be P1 cross P1 and the base to be P1 and B just one component, let's say S, where this S is a general curve of by a degree 2n. Then you can check that, in fact, you get an LCYF vibration, a local labial vibration, and then you can measure or calculate the degree of this S over the base, and you can see that that's precisely 2. And in fact, this is something that has to do with the fact that we are working in dimension 2. In dimension 2, in the setting of that theorem, the Stein degree will be universally bounded by 2. You cannot go beyond 2. And that essentially has to do with the fact that if something non-trivial happens, is because you have a P1 bundle. And if you have a horizontal divisor on a P1 bundle with this numerical condition, then the intersection of this horizontal component with the fibers cannot be more than 2. And that's because the canonical bundle of P1 has degree -2. So that's why you cannot go beyond 2. But if you go to higher dimension, then it's not that simple. The possibility that you get for the vibration is much, much larger than in dimension 2. Okay, so in the same work on moduli, I formulated this conjecture, which says that if you look at local labial vibrations of dimension D, defined over field of characteristics is 0, so we allow non-closed fields as well. And if you take any horizontal component of our boundary, not necessarily with coefficient 1, but just assuming that the coefficient is not too small, then the Stein degree of S over the base should be universally bounded. So this is harder than in the case of coefficient 1. In the case of coefficient 1, is a bit easier to do in induction using adjunction and so on. But when the coefficient is not 1, then this becomes much more complicated. But still, it turns out that this Stein degree is universally bounded, depending only on the dimension D and on T. In fact, I will tell you in a bit that this D, you can take it just to be dimension of the fibers. So it only depends on the relative dimension and this coefficient T here. Okay, so this is, of course, if you take K to be an algebraically closed field, then this you can view this as purely a geometric statement. But you can also consider non-closed fields. This K can be a number field, for example. Then this is telling something beyond geometry. It's telling something essentially number theoretic. It's an arithmetic statement. It says that, let's say if we take the base to be just a point, the spectrum of our field K, then this conjecture is saying that for any such component, the Stein degree, in this case, is precisely the dimension of the structure sheaf of this component over our ground field K. This should be universally bounded. So it tells something arithmetic. So in dimension 1, it's not difficult to see why this should be the case, let's say over number fields. But already getting to dimension 2 is quite non-trivial. But in higher dimension will be much, much more non-trivial. Okay. So this conjecture is kind of, again, connects algebraic geometry to arithmetic geometry. And in fact, it also applies not only to this kind of subsets, but essentially you can take, instead of components of B, say that if you look at any place, any component of your bad singularities, then you must have the same kind of bound on the Stein degree. Okay, so in particular, in the arithmetic setting, if your bad locus of singularities are, let's say, closed points, then this is saying that for all the closed points where your singularities are bad, you must have a universal bound on the degree of the residue field over the base. And that is, if you prove something like that, that's highly non-trivial. Okay, so this for now remains open in the arithmetic case, but recently with my colleague Santai Chu, we showed that in the geometric setting, if the field is already algebraically closed, then in fact this conjecture is true and there is a universal bound on the Stein degree. We prove even something actually stronger. We even show that if you normalize this S, so if you normalize S, the Stein degree potentially can dramatically change. But even that, we can bound it. So we can show that the Stein degree of the normalization over the base is bounded universally in terms of D and T. And another interesting thing is that if you don't assume this S or this locus to be horizontal, then this statement is not true anymore. In fact, we constructed counterexamples where this degree can be arbitrarily large if you don't assume horizontal. But still, a version of this holds. In particular, if your fibration is of a Fano kind, then this actually the statement is expected to be true. And in some cases, we prove that indeed, even without this horizontal condition, the statement is in fact true. So let's just look at one consequence of this theorem. Suppose that we look at this local area of fibration and S as in the theorem, and let's take F to be a general fiber of X to Y, and let's restrict S to this general fiber. So potentially you can have many different components. But surprisingly, this theorem implies that the number of these components, not even if connected, even the irreducible components, must be universally bounded. So that's quite kind of surprising if you look at, if you are given a statement like this without seeing the theorem. Okay, so for the remaining few minutes, I'm going just to tell you a few ideas of the proof of this theorem. So as I told you before, it actually relies on several very non-trivial ingredients, so it's not as straightforward as it may look. Okay, so this is essentially, I'm going just to give you a very rough picture of what is going on. So let's denote the statement of the theorem as H dt. The H is there because we are looking at horizontal components. So just to remind you of horizontal. So this is just the statement of the theorem, where now D is the relative dimension. But in fact, we also need the vertical version, but not in full generality because it fails, but instead we put a bit of more extra structure. We assume that the fibration has some sort of Fano structure. We also assume that these components S, if they are vertical, they map to divisors on the base rather than to an arbitrary subset. So that kind of simplifies the situation. But this, I think, in the end, this should not be necessary. Just assuming Fano type should imply all the horizontal cases. But anyway, okay, so the first step is to show that you can check the one-dimensional version in the horizontal case is more or less straightforward. And then the first step is to show that this implies the vertical case of relative dimension 1. And this is already, it has to rely on the so-called theory of complements and some quite non-trivial results from this theory. So it's not straightforward even in the relative dimension 1 case. But let me ignore the details here and go to the next step. In the next step, one tries to show that the relative 1 case in the vertical case implies basically all the other cases in the vertical case in higher dimension. And how this works, on the base, you can take hyperplane sections and reduce to the situation when the base is the surface and the image of S is just a divisor T, which is a curve. Here, you cannot take another hyperplane section to reduce to the case of base curve because, I mean, you have difficulty with the counting of the number of components of the fibers. Okay, and then at this point, we use MMP, the minimal model program, so another highly non-trivial ingredient, together with this theory of complements to basically set up to change our situation where we have some extra structures coming from this complement theory. This complement theory essentially, it says that you can go from a highly kind of more or less random setting to a setting where you have some kind of discrete information or discrete structure. So from that, you get another boundary divisor C, where it has controlled coefficients, so they are not arbitrary anymore, and it also has the same Calabi-Yau condition together with some even better singularity conditions. And moreover, this new boundary contains our components. Okay, so we reduce after some lengthy arguments with this setting, and then in this setting, okay, again, we use MMP to reduce to the situation where we also have an extra, even more structure, which is a Fano fibration, in addition to our local Calabi-Yau structure. Then we have to divide into two parts, depending on whether this Fano fibration is trivial or not, in the sense that the base of the fibration Z over Y, if the relative dimension is 1, then this allows us to do induction here by dimension. But it can also happen that this relative dimension is just 0, which is more or less, it means that Z to Y is an isomorphism where we are concerned. So that in that way, you cannot apply induction anymore. But instead, we look at the fibers and we show that these fibers actually belong to some bounded family. And this again relies on another quite non-trivial fact, so-called BAB. And then, so even that is not enough, we use this BAB so to show that general fibers are bounded. And then from here, we can birationally transform our map into a map where not only general fiber, but all the fibers are bounded. But then these kind of spaces that you get can be like highly singular, and it's very difficult to work with them. So instead of just working over this, we take another quite non-trivial ingredient. We use log geometry to transform this fibration into a fibration where the singularities are much better. More precisely, we transform our fibration into a toroidal fibration. course, one thing that we lose in this process is our, if you, like, you don't have any more Fano vibration, Calabi-Yau structure, and so on. You lose this global information. But at least locally, we have very nice singularities. And we take advantage of this nicer setting to control the Stein degree. So basically what we do, we look at the center of our original divisor S, now on the toroidal map, and that turns out to be a so-called low-canonical center of our toroidal setting. Okay, and then in this setting, again, we apply a few more results in birational geometry to show that, in fact, we can control the Stein degree of C of the center over the base, and finally, we also have to control the Stein degree of S over this center C, and then we put everything together, and then we get a universal bound. So you see that this already we use like 3-4 quite non-trivial facts in order to get our bound. Okay, and then finally, one has to go from the vertical setting to the horizontal setting in every dimension. And this again relies on kind of similar technology, so I'm not going to repeat it again. And finally, anyway, we put everything together and we get this universal bound for the Stein degree in the geometric setting. But as I said, the arithmetic setting is still missing here because we need to take care of also not of just the geometry, but also with the absolute Galois group. When you go from K to the algebraic closure, what happens to the geometry of the fibration? We have to control that, and that is quite also complicated, but I'm quite confident that that should be also settled in the not so distant future. Okay, that is the end of my talk, and thanks for listening.
Thank you for the beautiful talk. Any questions? Yeah.
So the way you get the bound on the Stein degree doesn't appear to be computable, or am I wrong?
Well, for now, at least the way we prove it is very non-effective. But of course, you can, as always, say, can you make it effective or not? Then you have to modify the proof. The current proof cannot give you an effective, because many of the ingredients are highly non-effective. So in lower dimension, I would say yes.
Can you say, for example, that the bound would be polynomial in D or in D and T?
That's hard to say. I mean, many of the bounds in birational geometry, when we try to calculate them, they happen to be like exponential or even much worse. So I'm not so sure. Maybe in lower dimension, one can get something reasonable. But I think if you try to get anything effective in higher dimension, it's going to be very, very large.
Other questions? Yeah.
Characteristic P.
Yes, in fact, one of my students is working on that in the positive characteristic. I'm sure he's somewhere here. He can prove many cases, but not still the full case. Yeah, if you only consider separable, that would be easier, but it's more interesting if you prove the full case. So for now, we still don't know whether it holds in the full generality case, or you have to put some extra assumptions.
Other questions? Okay, great. Thank you. I guess we'll take a break.
Thank you.
Oh, hello. It's my great pleasure to introduce today's second distinguished speaker, Bao Chao Ngo from University of Chicago. His Chinese name is Wu Baozhu. You may be more familiar with his Chinese name. Professor Ngo is a leading mathematician specializing in representation theory and number theory. He has proved the long-standing conjecture fundamental lemma. For this breakthrough work, he received a Fields Medal in 2010. Let's welcome Professor Ngo.
All right. Thank you very much for the kind introduction. Thank you for the invitation to this Congress. I've been very honored to be given an opportunity to speak here. So, all right. So I'm, going to get some more program, a modest program to generalize my former work on fundamental lemma to some new context. Because there's a lot of trace formula in automorphic forms that play increasingly important roles for the relative trace formula, and it's become very important to understand the endoscopic structures of the relative trace formula. So this is somehow a framework. Me and my student compute some range of examples. So we have not, have a complete theory yet. All right, so this is the, all right. But let me start with some very, go 50 years back with this very celebrated theorem by Narasimhan and Seshadri. When you have on the compact Riemann surface, then there's kind of bijective correspondence between unitary representation of the fundamental groups and polystable vector bundle of degree 0. Right? This is the very beginning of non-Navier-Hodge theory. So non-Hodge theory starts with when you try to replace unitary representation with complex representations. So if look at complex representation, P1 of X into GLN of C, then instead of polystable vector bundles, you have notion of polystable Higgs bundles, right? That is vector bundle equipped with some called Higgs fins, and that can be reduced to the unitary case when the Higgs fin equal to 0. And I think this is theorem due to Hitchin, Donaldson Hitchin for dimension 1 and higher dimension by Corlett and Simpson. So given this correspondence, we have on this the same set of complex representation of fundamental groups. We have two different algebraic structures. Where the one is given by kind of character varieties on the representation of P1 given by some generators into GLNC mode by conjugations. That is basically 5 varieties. And the other one is the kind of non-moduli space of vector bundle with Higgs fins. And that one is not a phi because the presence of the Hitchin fibration, which is map, which is a proper map. So it has many projective subvarieties. So what is kind of remarkable is this Hitchin fibration is because of these moduli space symplectic structures, and it actually have endowed completely integrable systems. So which is essentially map from M to A, where A is a phi space of half dimensions, and the fibers, the Lagrangians. And so from the algebraic point of view, what do you want to say that the generic fibers and essentially abelian varieties, and that can be made very precise by first by Hitchin spectron curve, and be more generalized by Bovin, Narasimhan, and Ramanan, who proved that MA can be identified with the compactified Picard of the spectron curve. Right? So the curve here can be allowed to be singular and reduced, but it had to be reduced. So we are very interested into this theory for reductive group G, not just for GLN. And for that, there's not quite the good analogy for BNR theorems. There's called theory of Cameron curve, which is a bit weaker, but there's no neat generalization of the BNR theorems. So we see how how you can overcome this. So now let me explain very briefly, and we come back with more detail later, what is relation to Langlands programs. So for vector bundles, instead of you can also study the modulus vector bundles of a curve of finite fins, right? And back to work by Harder and Narasimhan, you can try to count the number of vector bundles, maybe from on the over finite fins, and that gives you some expressions, and they have some kind of a recipe to derive from that counting things like Betty numbers, so the moduli space, for example, right? And now we just do the same kind of exercise, but instead of counting vector bundles and counting Higgs bundles, so vector bundle with a Higgs fins. So that is this kind of non-obvious question to ask, but when you ask, it's actually very easy to do. The answer is complicated, but there's no difficulty to solve that problem. Then when you write it down, you will write some kind of complicated expression that I'll show later, which is exactly the what we call in automorphic form the trace formula. I mean geometric side trace formula for Lie algebras, because and also the number of not just the whole moduli space Higgs bundles, but the fibers of the Hitchin fibers can also be counted. Number of points can be counted and give you the Auburn tegons. So what is the from the point of view automorphic form? Trace formula have this very peculiar structure called endoscopic structures, right? It's quite not very unfamiliar to geometers, for example. But for example, in the very upshot, I would say that the trace formula can be decomposed as the sum, and the sum will be indexed by conjugacy class of semi-simple element dual groups, right? So that is something that the right question is to how this kind of endoscopic structures appears on the geometric side of the Hitchin fibrations. So what it takes a while to realize, but what we want to do is to look at the Hitchin fibration denoted by H, and look at push forward the constant shift. That gives you some immense complex, and that complex must be decomposed in direct sum, parameterized by conjugacy, semi-simple conjugacy classes of dual groups. And this actually is not known by the people who are working on Hitchin fibration before. So that is what I want to explain this in this context, but also try to say how you can do it in very general context. And it is actually very much quite subtle invariant theory problems. So for Hitchin fibers, there are really two questions important. One is the endoscopic structures from automorphic point of view, and the other on dualities. And for Hitchin fibration is very, very neat and beautiful duality between the Hitchin fibration for G and for G dual. It's just perfect dualities. First discovered by conjecture by Hitchin, and then was proven later by Donaghy Pantev and over complex numbers, and by Chen and Zhu in generalities. And actually, the two statements, both the endoscopic structures and the dualities, can be treated in a very similar way. So then I'm going to explain. So now let me try to come back to this counting exercise. Let X be a smooth and proper curve of a fin K. Maybe K be finite fin for me. And G be reductive group over K. Actually, you can, in certain generalities, you can do group scheme over the curve, but it's not necessary for these talks. And so the Higgs bundles, G Higgs bundle is a pair consisting of G bundle E over X and Higgs fins. So Higgs fin is the global section, the adjoint vector bundle twisted by the canonical bundle, right? And so this is I just want to rewrite this in. I don't think this. Yeah, so instead of writing this, I want to write this in more complicated way. So here's the Higgs boson for me is a map from X to this quotient stack of the Lie algebra divided by the adjoint action, right? And the canonical boson come in as some kind of twisting, right? Because have a linear the scalar action on G that you can twist by the GM bosons associated to the canonical bosons. And it just this is not a theorem to be proven, it's just a definition. Higgs boson is just a map like this, right? So this is very convenient formulation. So for GLN, can replace by this fixed finished map from V to V trans by K. So now with this formulation, I can reformulate very convenient the Hitchin map. So this is okay for GLN. For GLN, you have this. I'm sorry. For GLN, you have vector bundle E and the Higgs fins at the Hitchin map would have A1, H2, AN. AI, the just characteristic polynomial of the Higgs fins. So in general, you look at this. So this is my main topic today is this map. This map from the quotient stack G mod G to the G mod mod G is called invariant theoretic quotient, which is just the spectrum of the G invariant function on the Lie algebras, right? So again, this is a stack. G mod G is a stack. You keep on the orbit and keep on stabilizers, and G mod mod G is a set, but it's just a set of subsimple conjugacy classes, right? And then of course you have a map from the quotient stack where you don't lose any information to this kind of invariant quotient where you lose some information. And by Chevalier, you have kind of several description of this quotient stack. Of course, one is the spectrum of the range of G invariant function on the Lie algebras, but you can also see it as a W invariant function on the Cartan and subalgebras. And also we know that this invariant this ring of invariants is a polynomial algebras, right? And A1, A2, AN are now certain homogeneous degrees of the degrees are the exponents of the Lie algebras, right? In the case of GLN, 1, 2, 3, and. All right, so this is the. So yeah, was just saying this. All right, now to make the point to connect endoscopy, let assume that the base fin is a finite fin, and now we try to count the Higgs bosons, and just do like very much by proceeding in the Harder Narasimhan. Then you see that the number of point of M is this expression, right? You have a sum of orbital integrons, and there's a kind of further sum, kind of Gauss homology of K1. So it's kind of technical thing that I want to ignore it for now. I have to write it because I don't want to write an incorrect formula, but basically you can ignore it. It doesn't really harm in any way. So if you start from G, you have to count not only for the group G, but on the inner forms of G somehow. So this is the K1. So on the strong inner form of G, which are locally trivials. And this can be infinite set, but only finitely many of them actually contribute non-zero terms. All right. From now, I just assume this K1 to be 0, to be just one element, to not to be bothered with that. And now I want to explain the terms. So this is trace formula. So you need some kind of test function, and the test function is this function. It's given by some canonical divisors. You fix some non-zero meromorphic section of your canonical bundles, and then that gives you some divisors. And this is then by using this integer to scale the OV point of Lie algebras, and then just put them together. Then you get your test function to be inserted into the trace formula. And then you have this. This is the number of point of M is the sum of these integrals, right? All right. And you have a very similar expression for the Hitchin fibers, right? Now we just look at the orbital integrals where gamma is some global conjugacy classes with a fixed characteristic polynomials, right? So again, this set can be infinite set even for SL2, right? This is some kind of very serious Galois cohomology going on. This set can be infinite. For GNI, just one element, but for SL2, there's infinite. But the number of non-zero terms is only finite. So all these kind of arithmetic problems that we can ignore for now. So this is the infinite set of the Galois cohomology of the centralizer. So so what is somehow better set would be the set of the gamma in G of A, adens, that have these characteristic polynomials, and there is the defect between the two sets, either the global conjugacy classes or adelic conjugacy class are measured by this obstruction group called some H1, some co-kernel groups. And this is usually a very small group, Z mod 2Z or Z mod 2Z times Z mod 2Z and so on. And in the theory of trace formula, what we do is to rewrite this sum using some kind of Fourier transform on these finite groups. And by this Fourier transform, that gives you a way to write your number of points as the sum of two terms. Right? Those terms seem to be more basic than the whole sum. Right? This is the so this is the thing. By doing Fourier transform on this, we have this H1 minus A is some O kappa A, and kappa is actually in the. Sorry, I some misprint here. Kappa be the dual of these co-kernel groups. So anyway, and then this kappa can be then identified with semi-simple class in the dual groups. And now the quite very sudden question is how this co-kernel group varies when A varies, right? This is depend on the Galois cohomology of centralizer and so on, and how we can translate this kind of sudden arithmetic decomposition into geometries. And this is the very basic question that I want to address. So as usual, when you have some kind of cohomologies and want to have some kind of canonical decompositions, the only thing you can think of, you need some kind of group action, some finite group action. Then you have your cohomology codified by the character of that groups, right? But there is not so much, when you look at the Hitchin fibration, you can see what kind of finite group acting on that, right? But there is natural thing that act on Hitchin fibration is the Hamiltonian action of vector fields, right? So Hamilton vector field doesn't give you any interesting decompositions on the cohomology because it's kind of connected things. So what happened is there's some kind of group schemes whose Lie algebras, acting on Hitchin fibrations, whose Lie algebra is exactly the Hamiltonian vector field action. and whose pi naught part will give the endoscopic decompositions. So now I'm setting out to try to define these group schemes acting on the hitching vibrations. So that is the pica actions. So again, this infinitesimal part of the pica action is the Hamiltonian vector fields. So for GN lengths, and that is kind of quite clear what we want to do, because by the BNR theorem, we know that the Hitchin fibers are compactified pica varieties. So the natural group acting on the pica varieties itself. So there's the pica group acting on the compactified pica. So in the case of GN length, that doesn't give you any kind of interesting decomposition, because the pi naught, the connected component group of the pica, is z to some powers. So there's no torsion part in it. But what happens if for other groups, there will be very interesting torsion part in the kind of pica actions. So that's what I'm saying. And then for other reductive group, the pi naught PA, they can define some kind of pica action canonically, and the pi naught PAs may have some torsion part, and the torsion part can jump around, can become bigger and smaller, and that is how I have very interesting decomposition of common-Hitchin vibrations. So the way that you can define this action, the pica action, is rely on invariant theory, I said. So in this case, this kind of usual Hitchin vibration is an invariant theory of adjoint action, and that the kind of central object called the regular centralizer that I am now want to explain. So now let G to be the Lie algebras, and let I to be the centralizer group scheme. That means for every element in the Lie algebra, I look at the the centralizers. So this look kind of not very nice group scheme. It's not flat, right? At 0 we have the whole group, and for regular semi-simple element have the torus, which is the rank of the groups. So so we want to make some nice group scheme. So let G red to be the open subset where the dimension of the centralizer is equal to the rank of the groups. So it can be a regular semi-simple matrix, or for example, regular nilpotent matrix. Nilpotent with only one Jordan block. They are all regular in that sense. So and then if you look at the this I could guide the characteristic polynomial map, right? Associating every matrix is characteristic polynomials. When you restrict this characteristic polynomial map to the regular part, you have a smooth map, right? And moreover, every fiber is actually a single conjugacy class. Right? Over 0, you have only one orbit that is the regular nilpotent orbit, right? And so here is the main. Actually, it's very simple, but when I discovered this thing 20 years ago, I couldn't believe that it can be such nice, simple. When you restrict the centralizer to this regular part, and then you get a smooth group scheme, and what happens? That smooth group descent to the characteristic polynomials. Right? So that is the what I call the regular centralizer, that descent, simple descent of the restriction of the centralizer to regular element. And moreover, when you put back, so because it is descent, when you put back J to array, of course you get array itself because it's a descent. But when you put back to the whole G, to the whole Lie algebras, then you have a smooth group scheme J. And what happens? Let's have a canonical map to I. So there's canonical map from the regular centralizer to I. So this is kind of fact that we have to do it to believe it, because you start from any matrix, right? And you look at these characteristic polynomials, and then you look at another matrix, which is the regular matrix, of that characteristic polynomials. Then I claim in that the centralizers of the regular matrix map canonically to the centralizer of the one that may not be regular, right? It's just the fact. So this is the, so when you have this, you can, so this kind of formatical invariant theory package that allow to define these kind of Picard actions. So when you have this for A and A, which is basically map from X to the to this A, to the invariant quotient, and then just put back your regular centralizer. You have JA, which is now a smooth group scheme over X, and then you should declare that your Picard stack is a torsor of JA, and then because you have this map from J to I, that gives you an action the PA on H minus 1 of A. That's it. So this map from from J to I is kind of universal thing that give rise to the action Picard action. Right. This is the all right. All right. So this is the so this PA is a smooth Picard stack, and now it's well defined, and you can some little calculation that give you the the Lie algebra is really the Hamiltonian actions. And then, but now what is very interesting actually the pi naught, right? The pi naught of PA is it does depend on A in some interesting way, and there's some kind of shift that interpolate on this together. And what here is the quite remarkable fact is that when you set down to calculate what is pi naught of PA, then you recover this complicated notion in automorphic form called endoscopic groups. So when the torsion part of pi naught PA jumps, and then when you hit some endoscopic groups, that is the basic statement. And to doing that, so for example, in the case of SM2, it's very simple. The SM2, but it's very simple and remarkable to the your Higgs boson is just a degree 2 vector boson with trivial line determinants, and theta is a Higgs fin with a traceless endomorphisms, and A is just the determinant of that Higgs fins, and so that give you some spectron covers, and then you can try to compute what is this pi naught of PA. Then you can realize that it's almost only 0, but it becomes 0 to Z exactly when after normalizing your spectron curve, you get some unramified covers, right? So that give exactly the two torsion of your Jacobian York curve. And now here is another point. This is a special case, but in general, you can do this calculation. It's actually not very hard. The example look quite magical, but the calculation is not so hard, and it really relies on the fact that you can realize A as there's this covering, T mod A, which is W flat covering. It's called Cameron covering in this theory. So yeah, so basically here that to do this endoscopic decomposition, you need two things. You need the regular centralizers, and you need the fact that the regular centralizer can be described by the way of these Cameron coverings. So this is the kind of roughly what we say that J is the very scalar reducible of the trivial torus, mod out, even by W, and this is almost an isomorphism. It is actually the open immersion, so there's only different by the connected component, and there's a very precise way to describe what the defect is, and this is that this defect is quite suddenly theoretical invariant, but first you can do endoscopy, but then you can use it to prove the duality of Hitchin vibrations. All right, so now as I said, the trace formula that appears here, the trace formula algebra, actually the simplest trace formula in automorphic forms. So there's many other trace formula that you really want to study. For the trace formula itself of the groups, right? Which is not base action, the adjoint action, but the conjugation of action of G on itself. And there's an action of kind of a symmetric space, right? And the action of the spherical varieties that have become relevant in the emerging relative Lagrange programs. And also for the not related to trace formula, when you look at the Hitchin vibration for higher dimension varieties that have an had to consider action on commuting varieties, right? So that is, at this point, I just want to consider any action. At some point, I had to restrict myself, but at this point, I just look at any action. So I have G, some reductive group acting on some Norman of 5 varieties M, and I look at the stack of map from X to M or G. So it's very similar to what Andrei Okunkov talked about yesterday. Of course, I have to do some twisting here, do some GM twisting, but I try to ignore it for now. So for example, we have this kind of relative, there's kind of symmetric space, and you have reductive group G with involution, then you have the usual G, the component G on P plus K, and you have action of K on P. So that is quite an example in the case of symmetric space. Then you have this, when you look at the Rion, the bona fide trace formula, that have kind of unfamiliar object, but actually very nice situation. When you start with a semi-simple, simply connected groups, there's some very universal object called the Weinberg monoid that contain G times some Gm to the R, and so you have looked at the action of G add on M by conjugation, and that kind of group action situation give rise to the big trace formula, and this has been pursued by some of my students, Butier, Jingren Chi, and Xiao Wang. And so we can look at the action of G on X times X, or cotangent of X, or X is fixed spherical varieties. That is relevant to the Sakelyaradi Venkatesh program. And then you want to look commuting schemes. For example, X is surface, then you look at the scheme of 2 elements in Lie algebra that commute each other, and with a diagonal action of G. And that's somehow some of the most difficult situation. And now you want to generalize the invariant theory that I set out for the adjoint action on this case to see how it looks. And actually, okay. So first, somehow what seems to be difficult is actually quite easy here. The sovereignty theorem can be generalized very well. The Lunar-Richardson theorem. So the assumption is now that there exists actually at least one regular, and so I call regular orbit the orbit with the maximum dimension, right? And I call it semi-simple with the closed orbit. So as long as there exists at least one regular semi-simple orbit, then kind of sovereignty theorem can be generalized. And so that is called Lunar-Richardson theorem. I'm not going to state it, but it rather, when you get that information, it is not, it kind of the statement that this is not easy, not difficult to find. And for the endoscopy situation, you want to also assume that the zone stabilizer is a torus, right? It has some kind of torus action. All right, so now here is the very important distinction. When you have action of G on M, you have the M mod G, so the categorical quotient or the invariant theoretic quotient, which is of 5 varieties whose coordinate function are the invariant function on M. Right? That are 5 varieties, and that we know that the point that of the 5 varieties classifies closed orbit, right? But the closed orbit are not very nice, where they're not forming any, not open subset. It's some kind of constructible subset. But there's some kind of another quotient, I call it regular quotient, which is more intuitive. You just remove on the, just keep the regular orbit, the orbit of the maximum dimension. It just delete on the other orbit. Then you can form a quotient, like a geometric quotient, right? Geometric quotient is just a set who, set of orbit, set of regular orbit, and you can give them some kind of canonical algebraic structures. But it happens not to be a phi scheme. It's not even a scheme. It's very often an algebraic space, or maybe even a delineation for stack. But let's ignore that. It's basically a algebraic space, right? It's not a scheme. But then you have a map from that geometric quotient, that regular quotient, to the invariant quotient. So the whole point is what this map look like, right? So in the case of adjoint quotient, it just happens to be isomorphisms, because for every closed orbit, there is exactly one regular orbit. For 0, you have the regular nilpotent orbit, but in general, it's not true at all. So now the whole, the difficulty in generalize this kind of invariant theoretic package of regular centralizers is to understand the geometry of the map from the space of regular orbit, kind of geometric quotient, to the categorical quotient, the space of closed orbit. So what map look like? So to give you a little hint, just think about the simplest case, right? It's not a Lunar-Richardson case. Then look at GM acting on vector space by scalar action, right? And then the closed orbit is just 0, right? And regular orbit are just lie. That's a projective space. So the map I'm talking about is the map from projective space to the point. So how this thing look like in general situation? Right? So this is what I try to explain. So this is the map they want to discuss. The map from regular orbit to the categorical quotient. And so what happened is this? So the regular centralizer, when you define it, it use some kind of descent exercise. You see that actually well defined on this regular quotient. It's not defined on the invariant theoretic quotient. In the case of adjoint quotient, you have kind of lucky that there's isomorphism, but in general, it's actually defined on this regular quotient. But you can still run the machine that I explained if you have this assumption. So we need kind of two hypotheses that I'm going to explain. One, if you can check that, then things should work out. So first one is that there is this M-G is not a scheme, it's algebraic space, but I hypothesize that they actually contain a projective scheme. So there might be a projective scheme that is proper over the invariant quotient. So this is typical the case of GM acting on vector space and the projective space marking the point. So in the case of symmetric space, quasi-split maps, and also the situation of the Weinberg monoid, the situation is like this. You just have the regular quotient is just the gluing of finitely many copies of the invariant quotient. So it's non-separated scheme, right? Like A1 with gluing with 2 points. So of course, you just choose one of the copy that gives you a map which is isomorphism, so it's projective. Right? So that is the case of the kind of simplest case. In the case of symmetric space, that is gluing of 2 or 4 copies. In the case of the Weinberg monoid, that can be n factorial copies. It's combinatorially complicated. But I think the most kind of very interesting case here is the clear commuting schemes. So in the case of commuting schemes, it takes some unwinding. They're not going to do it, but you can prove that the invariant quotient is the Chow scheme, classifying zero-dimensional cyclones on the plane, right? The regular quotient is something you don't know, some kind of smooth algebraic stack, but it contains the Hilbert scheme as an open subset. And now we have this map, this Hilbert to Chow, is a proper map, is a resolution of the singularity Chow map. So the, my conjecture A somehow is contained this Hilbert to Chow map as a particular case, right? So I don't know if it's the conjecture, because in some case, we are looking at arbitrary action. It cannot be, it's not reasonable. There must be some assumption. For now, I don't know what it is. I compute many cases, 90% it works, but some example it doesn't work, right? So that some assumptions have to be found. But at least in this case, very interesting case, GNLAN, you have Hilbert-Chow map, and that should give you a way to generalize Hilbert-Chow map for other groups than GNLAN. All right, so this is the. So I claim that, now I'm not going to have time to explain, but when you have this assumption, you can actually define the Picard action on your generalized in very very general situation of general Hitchin fibrations, that including many cases in the case of relative trace formulas and so on, even some part of the Hitchin fibration for higher dimension varieties, but much more than that. But now how to to have a handle on how to compute this, understand this endoscopic decomposition. You need to another thing. You need to have a description of regular centralizer by some Kagala descent, right? And so we need to cover covers. So that's why I need the second assumption. Is existence of so the hypothesis B is now that W covering, right? So you have this you have this regular quotient, and over the regular quotient you are given a smooth group scheme which kind of regular centralizers. So you just want to define that actually this regular subscheme coming from some covering, some kind of very generalized covering. Right? You want it to be flat coverings. Otherwise it doesn't make sense to take this kind of way descent with W invariant, and it should. So this is maybe just kind of wishful thinking to generalizing the adjoint action, but it turned out that in any case that you can compute it actually true. Right? In the case of for example, in the case of symmetric space, have been computed out by my student Tom Heimester, and in the case of very complicated of Weinberg monoid, this was not written, but it's basically hidden in some way in the thesis of Xiao Wang and Griffin Wang. But I want to point you to some very remarkable other case. It's the case of the commuting scheme, right? Where you have the Hilbert scheme mapping to a group scheme. And this W covering here is actually not just the whole, not yet the whole regular quotient, but the Hilbert scheme, which is open part of it. And this is actually a very deep theorem of Hyman. And Hyman, proved this kind of n factorial conjectures, which is basically just say that the existence of this covering, we call the Portresi bundles, right? And this kind of very singularity in the theory, because he proved he has very deep theorem algebraic combinatorics, and the statement they clearly have kind of geometric representation theoretic flavors, but the proof is very complicated with purely combinatorics. I don't think that people have tried very hard, but nobody really find the nice way to, the conceptual way to prove it. Otherwise, a lot of tableaus and stuff like that, right? So here that maybe give a hint, right? I'm not going to give, I cannot give another proof, but this is a way to generalize it. Right? This theorem of Hyman have the generalization in this context of the conjecture B for the in this group action. So I think that is all I have to say today. Thank you.
Are there any questions?
Can you say something about the case of general, sort of a general linear action, linear representation? You talk about the adjoint case in the beginning, but
Yes. I compute out even for GN2 with symmetric power up to sim 5 and sim 6. It seems to be working, but I have not computed further than that. Yeah. But there's one case which it doesn't work. Yeah. The case actually simple. The case that it doesn't work is rather simple. Just GN2 acting on GN2 times GN2 without committing assumption. Then the conjecture A is not true. So
the hypothesis A and B are not automatic in those cases.
It's not automatic. So it true in many cases that we the usual case that we study, but there's some case that is kind of very far away from the usual case we study that's not true. So I couldn't try to find a nice assumption to make sure that A and B satisfy. But they are that I think it's worth to study because it gives I think it's interesting to find the right theorem to imply A and B. Yeah.
Any other questions? So you formulated this general setting. I'm wondering in which setting, probably you put more assumptions or more cases, you can formulate like a fundamental lemma.
Well, I think the fundamental lemma is about you want to after you have endoscopic decompositions, then you have different pieces of two different groups can be compared, can be isomorphism, right? So here I'm not yet there, that I just want to find the decompositions. But for relative trace formula, there should be similar fundamental lemma. So once you have, I think on this, what I explained as A and B should work on the setting of spherical varieties, and then they should give you the endoscopic decomposition there. But there's a lot of work to be done. Yes.
Thank you. Any more questions? Okay, let's thank Professor Oh again.
So, good morning, everybody. So, welcome to the third lecture in this morning. I am Wenwei Lin from Shanghai Institute, CIMIS. It's my great honor to introduce you Professor Michael Jordan. He's the director of research at INRIA and Higher Normal School in Paris, and also distinguished professor at University of California, Berkeley. He's a member of National Academic Sciences and of Engineering, a foreign member of the Royal Society and the Chinese Academic of Engineering, and also a fellow of numerous prestigious society, including AAAI, IEEE, IMS, and also SIAM, so on and so forth. He also a receiver of IEEE John von Neumann Medal and the BBVA Frontier of Knowledge Award and the Wolf Grenada Prize. So his pioneering work is statistics, machine learning, variational inference, and graphic model forms the theoretical basis in this field. Yeah. So let's welcome.
All right, it's a pleasure to be here. Thank you very much for inviting me. So I'm going to give a somewhat unusual talk today. It's going to be about ideas and looking into the future, where I think there'll be mathematical challenges arising. So especially for the young people in the audience, you may perceive some new problems that you could start, by which you could start a new area. So I'm going to permit myself to do this partly because you're all interested in artificial intelligence. What is it? Where is it going? What does it mean? And all that. So that's part of my talk. Now, the mythology is that this field was created in the 50s, and there was very slow progress, and then finally there's a lot of progress. That's not really what happened. The AI problem, as it was posed in the 50s, is still open, making a machine reason like a human being. What has changed is that this field of machine learning had a major success story. And so I just give you a couple of pictures of people who led this about 30 years ago. So David Rumelhart developed the backpropagation algorithm, which is the underlying algorithm of deep learning. And Leo Breiman developed random forests, which were the big success story before deep learning, widely used in industry. And both of these algorithmic concepts reposed on huge data sources and the internet, which made that all available. So it's computer science wedded with mathematics that made all of this possible. The mathematics is basically gradient algorithms and some dynamical systems. It is possible to do a lot of mathematics with that, and it's still ongoing. I gave a plenary talk at the ICM a few years ago where I talked about symplectic geometry and how that relates to high-dimensional gradient descent. And so there is already a lot of mathematics in that. But that doesn't really capture the real spirit of what's happening in this era. What is really happening is that a vast new engineering field is being created, and it doesn't have many mathematical underpinnings. So I'm going to suggest what some of those underpinnings might be, and hopefully some of you will find that interesting. Okay, so the phrase AI was not being used until about 5 years ago. We were all saying machine learning. That was the main phrase, or statistics. But then we all know about LLMs, and all of you have tried an LLM, and you probably are very impressed by how good they are. They take in trillions of data points and have hundreds of billions of parameters. It's amazing. Okay, and it seems, because it's natural language that it's working with, and not just numbers and predictions, that it's a human-like entity. And so the phrase AI returned. But no new ideas were really present. It was gradient-based algorithms and very large sets of parameters, and working surprisingly well, but still, the underlying concept was simple. Now, we are being led by this phrase AI to believe that we are creating an intelligence, an entity, that we interact with, and it knows everything, and it may even be better than human beings. That's a super intelligence. That's not a good metaphor. Really, when I ask a question to one of the LLMs about general relativity, it'll give me a good answer. But that answer is probably coming from something that S.T. Yao wrote at some point. Okay? He contributed data which went into the LLM, and I'm now interacting with him via the LLM. If I ask a question about the best food in Paris, maybe S.T. Yao, but probably not. There's probably someone else who's written about the food, the restaurants in Paris. And now I'm interacting with them. And there's so many things I could ask, and I'm really interacting with billions of humans when I'm interacting with an LLM. So it's a collective. I'm interacting with a collective. But it's not just me, it's all of you too. It's a collective interacting with itself via the computer and via data analysis. Okay, so that's an obvious point in some ways. We're interacting in a collective. But when you say the word collective, you're led to thinking about economic mechanisms and equilibria. Because in a collective, the individuals are not just data points. They have goals. They have things they possess. They want to get value out of the interactions. It's a little bit more like a market where I go in and I want some value and I bring something and I trade and so on. That's really the more close to the future. And in fact, that's already the present. Lots of people in the internet are lying and telling weird stories and making up things and so on. And that all goes into the LLM. That can't be the future. All right. Moreover, no one's getting much value out of it. If I write a book or a song, it goes into the LLM, and the LLM people make the money. That's bad economics. All right. So what is the economics of the LLM-like architectures, and how do we start to build a mathematics that bridges between machine learning and microeconomics? That's my main point. All right. So in fact, LLMs really, even though they're very impressive, are lacking some fundamentals. They're very poor with uncertainty. They don't think about collectives in the design process, and there's very little focus on incentives. And I'm going to talk about all three of those today. All right, so uncertainty is something that is vastly important. Computers were developed without any uncertainty. It was logic was the mathematics. Von Neumann developed it on the basis of logic. And ever since then, it's been based on logic. The real world is not described very well by logic. There's vast uncertainty and vast change. It's better described by stochastic differential equations in 100,000 dimensions, something like that. All right? And so the computer doesn't think in those terms, in that mathematics. It thinks in a different mathematics. And the interface between computers and the real world has been very poor. And that leads to many of the problems we see to this day. All right, so we need to develop a new mathematics for the computer which interacts better with the real world. And already gradient descent and layered neural networks is not so bad. It's a good starting place, but it's definitely not the end. All right, so when you talk about uncertainty, it's this vastly important thing. All of us have different uncertainties about things, and we share our knowledge, and uncertainty goes down. Okay? LLMs don't participate in that process. They don't reason about uncertainty. They just say something. If you ask it, how sure are you that that term in Einstein's equation is correct, it'll say, I'm very sure, and it'll give you a long reason. Very sure. If you say, well, no, you're not right because something else, it'll change its mind completely. Right? And you can do that on any topic. It's not reasoning about uncertainty. Okay? And if you have a doctor that you're interacting with and you say, what's wrong with me? The doctor says, I think you have heart disease. And you say, well, no, I don't think that's right. And it'll change its mind and say, no, now you have liver disease. That would be a pretty bad doctor. And that's what we have with LLMs right now. Okay, there's lots of work on this topic. Conformal methods, e-processes, all kinds of sampling methods. I work on this too. There's lots of work in trying to endow networks with uncertainty. But it's only getting at a very small part of the problem. And what's missing is the economic perspective. Okay, so first of all, let's think a little bit about collectives and uncertainty. Uncertainty is not just, I gathered some data and I have an error bar that goes as 1 over square root of the number of data points. That's classical statistical uncertainty, but it's a bigger problem than that. So just think about a very simple problem where I've got a duck, and the duck is deciding today which side of the pond to go to get food. And the duck is a very good statistician, so in the past, the duck has analyzed all of the data and knows that there's 2/3 as much food on the left and only 1/3 as much food on the right. And so now the duck is trying to do an optimal Bayesian decision calculation, maximize its utility. What should it do? Well, it should go to the left with probability 1. That maximizes the chance of success. Real ducks don't do that. Real ducks, surprisingly, do something called probability matching. They go to the left with probability 2/3 and to the right with probability 1/3. It's suboptimal. You get less food by doing that, right? Humans also do this. They probability match in lots of situations where they shouldn't. It's one of the flaws, supposedly, in human probability reasoning. Now, is this really a flaw? Okay, if you were to put a rule, Bayes' theorem, into the LLM, it wouldn't do this. So should we just put Bayes' theorem into the LLM? Well, no, because the real setting is to think about the collective. What if there are many ducks? And that's, in fact, what evolution worked with. It was never just one duck. There were many ducks. If every duck goes to the left, you have an unexploited resource, and the overall social welfare, amount of food eaten, is low. You can now think about an algorithm which distributes ducks to food optimally, some dynamic program, right? There's an optimal algorithm which is extremely simple. Each duck randomly and independently goes left with probability 2/3 and right with probability 1/3. That's a Nash equilibrium, a Bayes-Nash equilibrium, okay? And evolution could easily have discovered that, and it did. All right, so the point here is not to analyze ducks. The point is that what we mean by uncertainty and optimal decision uncertainty depends on the context, and it depends on the collective. LLMs don't know any about that. We do. When we reason, we do this kind of thing very, very naturally. All right. So it's not so clear how to improve LLMs to do this. It really requires something really quite different than what they currently have. All right, so that's one issue of uncertainty. Here's the other one, which is even more economics. So if I'm interacting with you and you know something I don't know, you have a skill that I don't have, I would like to ask you to perform your task, okay? And I may offer you some payment in return. All right, and I know something you don't know. So there's a asymmetry of information. It's asymmetric. Okay, this is very common in economics. Nash equilibria are symmetric. What we're talking about here are what are called Stackelberg equilibria, an asymmetric equilibrium, just for the game theory. Okay, so if you know something I don't know about how good you are to do some task, I may say, how long will it take you to do the task? You say 10 hours, okay? And I'm going to pay you for 10 hours because I believe you. But really, you know that you're much better. You can do the task in 1 hour. So you do the task in 1 hour, you sit around for 9 hours, and I pay you for 10. Obviously, you're incentivized to not tell the truth. All right, so now you start to say, well, that's bad. Is there mechanisms under which I could actually incite you to tell the truth? Okay. And auctions are an example of such mechanisms. We all go in and give a bid for a painting. We don't overbid or underbid, and it's because it's a Nash equilibrium, okay, to tell your truth. That's called the Vickrey auction, all right? And there's also mathematics of asymmetric equilibria, and I'm going to be talking about that. It's called contract theory. Now, this is a kind of uncertainty which will never go away. If I ask you how good you are, you're not going to tell me exactly how good you are. I will never have the error go away. So it's different from statistical uncertainty, and it's equally important in the real world. When I interact with all of you, you know things I don't know, and you may or may not be telling me the truth, and I need to develop mechanisms to ensure some truth-telling. This is not happening on the current internet, and it's not happening with LLMs. And it's one of the reasons there's so many problems, and there will continue to be until we change our mathematical point of view. All right, so what's missing is in microeconomic perspective. We have big data from computer science. We have statistical gradient optimization algorithms working amazingly well at scale. What we're missing is the microeconomics of all this big system. Okay, so we've got to do this. We got to start to put this in machine learning blended with microeconomics. And so let me pause for a minute on this slide. This is an important one for the mathematicians. This is actually what I've been working on in the last 10 or 15 years. And so you'll see some words there that are familiar from more the machine learning side and some that are more economics, and there's a blend. The first slide is real important. What we have actually achieved mathematically, one of the things we've achieved in machine learning is to analyze stochastic differential equations and stochastic gradient ascent in millions of dimensions. Millions of dimensions. Manifolds and non-manifolds and so on. And we're able to do things like tell you that for a non-convex problem, even if there are many saddle points, we can escape the saddle points with a rate We have a lower bound and an upper bound, and the rate is polylogarithmic in the dimension. Okay, that was a discovery that came out of my group a few years ago. All right, so we have very strong results there, and there are necessary and sufficient conditions, and it's quite satisfying for non-convex problems. Now, trying to put that into economics doesn't really get very far, because economics is not about optimization, it's about equilibrium. Okay? We're not going to find something that's perfect for me or for you. We're going to find something which is an equilibrium between the two of us. What kind of mathematics do you need for equilibrium? It's not optimization. Gradient algorithms, when there are fixed points in a flow, do not find the fixed point. There are other algorithms which do. Gradient algorithms can spiral out. They're terrible in fixed point problems. There's something called extra gradient, which does spiral in. So if I have a fixed point and I have circular flow around it, and I start someplace, if I follow the gradient, I'll just follow a circle in continuous time. If I discretize it, I'll spiral out. Very bad. But there are algorithms that will go to the middle, to the fixed point, and they sort of tilt in a little bit, and that's called extra gradient. And so they exist, but they're not nearly as well studied in high dimensions and with stochasticity and so on. Right? So this is an older topic in mathematics, but is being brought to the fore. So nonlinear functional analysis, degree theory, and so on and so forth, that's the relevant mathematics here. That's not being used, but should be and will be soon. So we need to do equilibria, and we need to do this in high dimensions, not 3 dimensions, not 10, hundreds of thousands to millions or more. Okay, so that's where the mathematical challenges arise. I'll be talking about some of these other topics about asymmetries, uncertainty quantification, and so on and so forth. But the point is that there's a lot of topics here. This is not what most people in machine learning are working on. They're working on building these big systems and doing empirical tests of things. And it's exciting and it's interesting, but there's very little mathematics in it and very little understanding. To me, these are the topics that will lead to understanding. Okay, so let me tell you now about some little research vignettes, particular results, and I'll actually get to a theorem or two along the way. I'm going to go to something a little more mathematical, just to give you an idea of how you can make these things formal. All right, so the first thing I want to talk about is bias. Bias is hugely important in these very, very large systems. Any learning system is going to have a large bias, and you need to control that somehow. In statistics, we're used to saying there's no bias or little bias, and we have a lot of variance, and we control that in some way. In the new world, it'll be all about bias. All right, so let me show you an example of this. This is AlphaFold. So as you may know, Nobel Prize was given for this work. It is very important and impressive. It is machine learning. You take a sequence of amino acids, and it will predict the structure of the folded protein. And it does it extremely well, better than any previous system by a significant degree. Now, that means you can take amino acid sequences and get hundreds of millions of structures from AlphaFold. Huge number. Currently, if you try to crystallize in a laboratory amino acid structures, we have hundreds of thousands of known structures that really real science is done on the right. All right, hundreds of thousands, doesn't that sound like a lot? Well, no, there's so many proteins. Every virus, every bacteria has its own protein, and understanding that is critically important for biology. So we're not even close over on the right. So people are saying, well, why don't we just use AlphaFold to generate proteins and not worry about nature? Use it because it's a good mimic of nature. And this is often called AI for science, and I'm going to show you some problems with it. Okay, so here's an example of a study that was done in 2004, an important study in biology. It got a prize. People were studying whether, so proteins mostly, amino acid sequences mostly fold into something enzymatic. It's a nice folded structure, but occasionally there are quantum fluctuations, and there's strands hanging off that are fluctuating. And that used to be viewed as a broken protein. It would never be used by evolution. But it turns out that those strands, if you put several proteins next to each other, they can actually aggregate and make grill-like structures. And you put them in the membrane, and they can control flow in and out of the membrane. That seems to be the case, and it's being studied heavily right now. So these people in 2004 thought that might be a possibility, so they studied it. They took all of the proteins that were known, and they made a little 2x2 table. Quantum fluctuation, yes or no. Active in the cell, yes or no. Phosphorylation, okay? And that's a little 2x2 table that came from a huge data set, but it's just a 2x2 table. And a statistician could look at that and say, is there a statistical association between the rows and the columns? okay? And you calculate something called an odds ratio. You look at the null distribution, and you see if the data are out of the tail or in the middle of the distribution. Classical statistics. So they did that, and they found there was no evidence of an effect, okay? So a few years later, someone came along, and they said, let's not just use the existing data. Let's use AlphaFold. That's the green over there. We use now hundreds of millions of predicted structures, not real structures, but predicted ones. And we form the same 2x2 table, and we do the same test. And now they got a result that was significant. It was out in 6 sigma land. So they said, definitely there is an effect. All right. Now the problem is that this. So I'm going to spend a minute on this. The x-axis here is the odds ratio. If it, in this 2x2 table, you basically compute the diagonal versus the off diagonal. It's a little ratio. Okay? If that ratio is 1, there's no association. If it's bigger than 1, there's an association. All right. And so what we did, we redid this entire experiment. We took all the data, and we took half of it and did a Monte Carlo run on that to get a ground truth. And then we redid the experiment on the other half. The ground truth is the dotted line. So it seems like the odds ratio is probably around 2. Okay? The gold band right there is a confidence interval for AlphaFold. Okay? So it says the true odds ratio is around 3. And I'm very, very sure of that. Very small confidence interval. Okay? The problem is the truth is not in that confidence interval. It's too sure of itself, like most of the machine learning architectures, way too sure of itself. All right, so you could say, forget AlphaFold. Let's go back to what data we really have. We had 100,000 in the past. Now we have more. And so let's put that into a classical statistical analysis, and you get the gray error bar. This is the kind of thing we're used to in the past. It covers the truth, which it is guaranteed to do mathematically, right? But unfortunately, it also covers 1, which says you cannot reject the null hypothesis still after 20 years. Okay, so these are important problems in science to make a really hard decision. Bose, Einstein or not, or enzymatic or not, and so on and so forth. So long story short, we were able to fix this problem. So we have a method which is new. It's not in the classical statistical literature. We call it prediction-powered inference. And it is able to take the AlphaFold confidence interval and add a little bit of ground truth data, not much, and it will shift the confidence interval over to cover the truth, provably, and it'll grow a little bit. And that's the green interval. So you can see the green interval fixes the problem. It is much smaller than the gray one. It doesn't cover 1, so you can reject the null hypothesis. There really is an association. And it covers the truth provably, just like the gold region. Okay, so we did this kind of experiment in many, many domains, in astronomy, and ecology, and voting patterns, and so on and so forth. And we found the machine learning methods were always way too confident. They had very small confidence intervals, but they weren't covering the truth. Okay, now why is that? How can that possibly be? First of all, this is being done all over the place in this AI for science world. You will find hundreds of papers each week on it. And here's the problem. On the left, you see the prediction for a particular sequence for AlphaFold. And on the right, you see the actual experimental structure. All right, you can see there's quantum fluctuations, which are leading to those strands. AlphaFold completely missed it. How can that be? AlphaFold is really, really accurate. It got a Nobel Prize. And the problem is that it doesn't have much data on quantum fluctuations because people in the past didn't study it very much. The data is all about the past of science. And AlphaFold is really good at that. But most scientists don't want to be on the edge of science. They want to do new things. So they're asking questions. They form little 2x2 tables on new phenomena. AlphaFold is uniquely bad at that. And it gives out extremely bad confidence intervals. And that's not just AlphaFold. That's most of these AI for science projects. They're good at the old data, and they have high accuracy, and they're bad at new hypotheses. And the whole point here is that that's a problem, and it can be corrected with the appropriate statistical methodology. Okay, so here is just a little bit of the derivation of this for those who are interested. We have a paper in Science where we do this in many different domains, and then we show you how to derive this new estimator. And just briefly for the more probability-minded people, here's an example where we do something called M estimation. We're minimizing the expectation of a loss function, and therefore you want to probably form the gradient, which is also called the score function, the derivative d theta of the loss. And now the definition of an M estimator is the expectation of G is equal to 0. So we add and subtract a term. We take the expectation of G and we add and subtract expectation of G with F, which means alpha fold. We add and subtract that, and then the other expectation of G is the statistical analysis. All right, so now we can estimate each of those terms with statistical methodology. The first one is a point estimate we can get from AlphaFold. Just run it many, many times and get a point estimate. The second one is something we call the rectifier, and that can be estimated with a fairly simple concentration inequality. All right, so we get a point estimate and we add and subtract a set. And that took the original set and it moved it to be in the right place and made it a little bit bigger. Okay, so anyway, you can look at the details. It's not complicated. And we're able to prove a theorem which says that the probability you cover the truth with the new estimator is bigger than 1 minus alpha for any alpha. Okay. Okay, so that was the first little vignette. Now I'm going to move to things that are a little bit more economics oriented. Learning aware market design. Market design is a part of economics. It doesn't have any learning in it, and so our goal here is to put some learning inside of economics. All right, so here's an example of a real-world problem I've worked on. I'm involved in a company called United Masters, which links musicians to brands and listeners. It's a three-sided market. Musicians are making songs, they're putting it on the internet, and the classical model is just that gets streamed to people, and the musicians are not making any money. Okay, and that's a problem. So this is a new market where there's recommendations being made. The musicians are making songs, they're being recommended to listeners, but also brands are interested in having music associated with their brand. Something like the National Basketball Association has music. When you go to the website and watch a clip, there's music. And the music should be appropriate to the venue, and the NBA wants certain kind of music and not other music. All right, so there's a recommendation system, a data analysis system that predicts which musician will be popular on which website. And when that music is played, the musician gets paid. Moreover, other brands see that a certain musician is popular on a certain website, and they see that demographic is something that appeals to them. So if people go to the NBA website, the same people may be interested in tennis shoes. Okay? And so it is a three-way recommendation system with market dynamics, and it has an equilibrium. And you try to find that equilibrium with algorithms that are fixed-point algorithms. All right? And so that's what's being done in this company. And this company is actually successful. It has 3 million musicians signed up in the United States and hundreds of brands. And there's actually money flowing across these links, actual musicians who are actually making salaries. Okay, so I don't want to get into the details about the algorithms there, but I do want to do it for a different model. This is something that we call a 3-layer data market. It's with my colleague Ali Reza Falah. It's one that should be familiar to you. Many users will go to platforms to have a service. For example, Alipay. All right, so I go to Alipay and I get a service, which is the payment is made. All right, and other things happen. Moreover, Alipay gets data from me, and they use that to improve their service. So that's good. That's a positive feedback loop. All right. The problem is that Alipay and other entities often don't make enough money from the service. It's a small fraction of the payment of the transaction. So they sell their data to third parties. Right? Why would they do that? Well, third parties are interested in data so they can do prediction of the market. They can decide there's a new restaurant needed or some other service. So the third parties are giving money to the platforms. Now, the problem is the users have lost something implicitly. They've lost their privacy. Their data is now being sent to an arbitrary third party. Many people wouldn't like that. Right? So we're now out of equilibrium. The users might learn about that and they might walk away. All right. So there are privacy mechanisms. There's something called differential privacy, which is when I send data to you, I add some heavy-tailed noise to the data so that you can't do certain kind of queries on my data. You can't learn certain things about me. So that's a mathematical theory. It was used in the United States Census this past year. It's been used quite widely. All right, but it's just the question is how much noise to add. If I really want to ensure my privacy, I want a lot of noise. But that's not a market. I got to do that in the context of other entities. So here you can imagine that Alipay and MasterCard or whatever decide on their own how much noise to add to the data. And then they advertise that. So say that Alipay will add exponential noise with a parameter 0.5. And MasterCard will add it with a parameter 0.1. All right? So Alipay is protecting your privacy much more. The other one is not. So now probably more users, when they learn that, will go to Alipay, and they will not go to MasterCard. That's good. Alipay gets more data, and they're happier. Now the problem, though, is the data buyers will not want the data from Alipay because it's noisy. They prefer the high-quality data from the other company. All right. So now there is an equilibrium computation. What will be the equilibrium of this overall system? And will it be a function? How will it be a function of the data collection process? Okay, so hopefully you get a hint of how that will work. You write down some constraints, you write down some statistical formulas, and you write down a Stackelberg equilibrium calculation, and it becomes a big nonlinear differential equation. Okay, and you can solve that for various choices of the parameters. The parameters might be, is there a minimum level of privacy the government wants to assure? Or is there a maximum level? Or what, many gross macro parameters that could be imposed on this system. All right, and so you can do that. Here's our little model. It's a statistical model, but put into an equilibrium calculation. Okay, and we can actually make predictions out of this by analyzing it as a Stackelberg game. So if you do game theory, you form game trees, and then equilibria are often found by going backwards on the game tree. And you can do that here and get explicit predictions about how this market will behave as a function of how much data and how much quality of data. Okay, so this may sound easy or natural or whatever. It's not being done at all. Okay, and it's not that easy because it's very nonlinear, and you want to do this in the context of a dynamical system that's actually changing. Okay, so I'm going to skip that, but you can now talk about regulatory concepts, help the government regulate in a mathematically sound way, not just by imposing arbitrary regulations, but regulating the equilibria, not regulating the algorithm. Okay, so I've said the word market a couple of times, but let's now say it a little more clearly. What's good about markets? And let me just say personally, I learned what's good about markets more from my experience in China than from my experience in the United States. I first came to China in the 1980s. I watched the Shenzhen experiment happen, and then I got involved with the Ant Group, Jack Ma's company, and helped them design their Alipay marketplace. And I watched how effective that was. And it was effective because it was a two-way market. It was not just a platform. You had users like you and me using Alipay, and you had merchants on the other side. And both sides had input into it, and they were connected by the market. That was very powerful. It was why Alipay to this day is a big success. It's a two-way market, not just a platform. In the US, we had PayPal and other systems. They were just a platform. It was not a market. Okay, so I learned about this from Jack Ma and others. And so if you think about AI systems, I think this market metaphor is an appropriate one. You have many players who have many conflicting objectives. They all coming together, and they know things that each other doesn't know. What are the equilibria of that system? How do we regulate that? That's the right way to think about this. Okay, so the last part of the talk, I'm going to talk a little more about I'm going to get to a theorem. I'm going to start with the theory of incentives. So this is an area of economics. There's been Nobel Prizes for it. It's a very important area. It's this thing I've talked about. Agents have private information, and a principal wants to incentivize them to take actions that the principal wants. Okay? And the goal is not just for one person to make money. The goal is for the overall system to have high social welfare. Okay, that's the design goal. Okay, so you know of examples of this. So the airlines in the 1980s, when I was a young person, you would pay one price to go on an airline. There was not different fares. You would pay, 1,000 RMB, and you would have a seat on the airline. Just like in a movie theater, you pay one price for everybody. Many of you will not remember that, but that was the case. It seems strange now. And so what would happen to the airlines is that often there would be only a few people on the airline, or there would be too many people. It was not good regulation of allocation. And so the airline was thinking, how can I understand for each person how much they're willing to pay? It's a classical economics question. If I look at you, I can say, well, you're a professor you're dressed very nice, probably you have more willingness to pay. But that ain't be the case. You may be on vacation, you don't care. Where someone else, a young student, might really need to go to Beijing because there's some illness in the family and they really need to get there. They're willing to pay more on that day. And the overall system will not know that. So how do you design a system that will still fill the airline and make everybody happy? All right, and so what that system is, it's called contract theory. You have different services and different prices. You have a menu of options. This service, this price, this service, this price. And there's a big list of them. And each person individually looks at that menu. They all get the same menu. There's no discrimination. And they pick one of the options for them in that moment that only they know is a good option. All right, and tomorrow they may pick a different option. And the menu is designed in such a way that the overall flow of customers and revenue is high. Okay, and so the airlines started doing that in the end of the 1980s, and that saved the airlines from disaster. They were all going out of business because they were not able to fill their airlines. All right, so contract theory is asymmetric information flow. And so what the last part of my talk will be about is what we call statistical contract theory. Contract theory is usually designed with no data. It's just someone thinks for a little while and they write down the menu. Okay? Someone at an airline. All right, so we would like to now think about a statistical contract theory. And I'm going to motivate this in the domain of clinical trials. So, for example, the development of a new drug or a vaccine. And in the United States, at least, there's an entity in the government called the FDA, which regulates which drugs go to market, which are given to people. And they do that by doing several phases of trials. They try the drug on a control group and a treatment group, and they do that over several years. And they decide whether the drug really is good and should go to market or whether it's not. But they make errors, obviously, it's statistics. So there's some false positives, drugs that shouldn't go to market which do, and there's some false negatives, drugs that should go to market but don't. And they want to minimize the false positives and false negatives. So that's statistics, and they're very good at that. But the system is not very good overall, and I want to talk about that. The reason is because it really is a principal-agent problem. The principal is the regulator, like the FDA, and the agents are like the companies that are proposing new drugs. Okay? Now, the agent, the company, knows more than the principal. The government does not know about the details of a particular drug, how good it was in previous trials, how related it is to some previous drug, and so on. They don't know all kinds of details. And the companies are not motivated to tell the government. And the government can't just force them to tell them. That's the problem in economics. All right, so you need to design a menu of some kind. But what kind of menu? Because the goal here is not to just have high revenue. The goal here is to control statistical error. Something very different. Okay? In fact, if the FDA proposes, I'm just doing good statistics, and they tell everybody how they're doing it, then that leads to people gaming the system. Oh, if you're doing it that way, I can lie a little bit and have more probability of getting my drug to go to market. And that's what's happening in real life. Okay, so to summarize the statistical problem, let's imagine there are bad drugs and good drugs. Theta is equal to 0, theta equals 1. And let's imagine the statistician designs a protocol for which the probability of approval of a bad drug is low. That's the false positive rate. And the probability of a approval for a good drug is high. That's called the power. That's being done by the FDA. The problem is that in real life, the financial incentives are not aligned. So let's imagine a small profit was to be made. Let's suppose it costs $20 million to run a trial. And if you if you got the drug to go to market, you might make $200 million. Okay? So in that company, you can do a calculation. What's my expected profit if the drug is actually not effective? I don't know that, but it might be. All right? But I'm going to make minus 10 million expected value if the drug is not effective. Every time I send one in, I'm losing money because I have to pay the cost of the trial. So I'm not going to do that very often. I'm only going to send really trusted drugs into the FDA, the regulator. That's good. The FDA is mostly receiving decent drugs, and they do than a approval process, and only the best of the best go to the market. That would be a good market. The problem is on the right is more like reality. It costs $20 million to run the trial, and if it goes to market, maybe you make $2 billion. Okay, and now the incentives are bad. The expected profit, even if the drug is not good, is actually 80 million. All right, so the CEO of the company looks at that and he says, send all of the possible candidates into let's put them in to the process, because there'll be some false positives, and we'll get a little more money from that, and that'll help us. This is not unethical. It might be viewed a little bit unethical, but it's just what people do. All right, so now can we make some mathematics that will make this not happen? All right, and so we are able to do that. So we have a new theory called statistical contract theory. And briefly, here is a contract. If you're a company and you come to this, you opt in to do this contract, or you walk away. You say, I don't want that. That's part of the mathematics. If I opt in, I pay the price of the trial. It's called a reservation price. I pay some amount to play the game. Then I choose a payout function. What is a payout function? It's a measurable function of the data. It's how much money I will get if the data come out in a certain way. If the data come out in a different way, I'll get a different amount of money. It's my choice of how I'll be rewarded. Okay, it also has it at licensing terms, how many cities I can be in, what kind of people I can do it in, all the kind of things that regulators want to impose on you. So you choose something that has good licensing terms and has high revenue from your point of view. Now, in that moment, you're using your internal knowledge that the regulator does not know, but the regulator is thinking about it. Okay, so you choose F from a menu of options. That's the contract theory. And it's our job as mathematicians to design the menu F. What functions? What measurable functions of data? Not just any functions will do. And I'll show you an if and only if statement, a characterization of the functions. Then a statistical trial is run. You sample from nature. You get the data, Z. You put that into the function. The company gets the payoff, F of Z. They picked F, but then Z comes from nature, and they get a reward. Okay, maybe it was good, maybe it's bad. And then the principal gets the utility, which is the negative of that, okay, basically. That's a system now. It's a closed system. You can write all the equations and find the equilibrium of this system. All right. Okay, so I'm going to state a theorem on the next page, but just let me give you the terms that are needed for the theorem. The economic goal in these systems is what is called incentive compatibility, which just means that all of the players, the principal and the agent, should not have positive expected benefit. If you take benefit minus cost, it should not just be they get free money for nothing. That would be called arbitrage, and you don't want that. Okay, so you want everybody to have zero or negative expected value. That's called incentive compatibility. So it's an expectation of various parameters in the system, therefore it is a polytope. Okay, so we're on a polytope of some kind. The statistical goal is now new. It says on that polytope, minimize the false positives and the false negatives. Okay, and that's now a functional of the underlying probability distribution. That's a nonlinear functional. Okay, we're probably doing it non-parametrically, meaning it's a nonlinear functional. All right, so that is the problem you need to solve. And now what we want to do is find a menu which makes this problem as good as possible. So the solutions it delivers are as good as possible. Okay, so finally, some actual mathematics stated in mathematical terms. We have a theorem which says that a statistical contract is incentive compatible, that's the economics, and controls the false positive rate, that's the statistics, if and only if that menu of payout functions are all non-negative super martingales. Okay, so where is that coming from? Well, super martingales are stochastic processes that want to drift down. Martingales don't drift anywhere, super martingales drift down. If they're non-negative, they tend to drift towards zero. Non-negative super martingales can use to test null hypotheses. You can set one up such that under the null hypothesis you drift towards zero. You have no evidence against the null, and over time it doesn't get any better. Whereas the same non-negative martingale, if the null hypothesis is not true, could grow exponentially. There's a separation between non-negative martingale versus exponential growth. These ideas originated in portfolio theory and finance. Optimal portfolio theory by Tom Cover started to do a little bit of this. And what we're doing is importing this into statistics and economics. Okay, so non-negative martingales are not that complicated. There are betting protocols which you take sums and products of terms. There's a little algebra of non-negative super martingales. And now we have an if and only if theorem, that if you use them, you will get incentive compatibility. And if you don't, you will not have incentive compatibility. The system will be gameable. So now we have a theory to deliver to the designers of these kind of economic systems, which says, here's the mathematical objects. It's called non-negative super martingales. You better learn about them. Just like people in the finance community learn about Black-Scholes and Brownian motion, now in this community, you'll need to learn about non-negative super martingales. And that's the vocabulary. All right, now there's brand new mathematical challenges that arise if you start studying these systems. And here's one of them. You can ask which non-negative super martingales have optimal power for composite alternatives. Let me just say what that means. In statistics, you have a null hypothesis, and it could be a point or a composite, many different possibilities. And you have an alternative, and it can be a point or it can be many possibilities. In classical statistics, null single versus null alternative was solved 40 years ago, 100 years ago. Composite null and one alternative was solved along the way, maybe 20 years ago. Composite versus composite is mostly still viewed as open. These non-negative super martingales solve that problem. Okay, it's a bit of a breakthrough. You can solve in an optimal way composite versus composite. Okay, and so now you can design martingales which for the null hypothesis will go to 0, and they will go exponentially for the alternative. So that means over time you can look at the outcome, and at some point it's big enough you could say I definitely am sure that it's the alternative. All right, and if you wait a little longer, you'll be even more sure, and it's possible to change your mind. That was not true in classical statistics. You had to make a decision once and you're done. In these systems, because of optimal stopping properties of martingales, you can actually change your mind. Okay, so anyway, it was now an open problem. We now know some super martingales, and they do have the right properties, if and only if, but which ones of them are optimal? Okay, and it turns out that we were able to solve that just this past year. This is a recent paper. The answer is a characterization of something called E-processes, and it involves a quantity known as the portfolio regret. That's a deterministic quantity. If you minimize that, you will be guaranteed to have an optimal stochastic decision in this martingale setting. Okay, so I'm going to finish here. I had a couple more slides which I'm not going to cover. I want to leave time for some questions if there are any. What I wanted to kind of introduce you to is some ideas that came from the last century. People like Kolmogorov and von Neumann and Wiener and Arrow all worked on these kind of things. But they're given brand new meaning in this world of the internet with vast amounts of data and new services emerging. All right, in fact, I want to go down to my final slide, which I'm going to skip over this stuff on. I had some stuff on how do you come up with metrics. I want to skip that. And my last page, yeah, here we go. So what I think this new field of this thing called AI is that every 50 years or so, a new engineering field emerges that changes humanity. So 50 years ago, chemical engineering was the biggest thing. My father was a chemical engineer. Many people in that era were chemical engineers. Chemical engineer didn't exist before the 1930s. Okay, it came up over the 40s and 50s. All right, people tried to build factories before that, but they didn't work very well. Now, before that, you had chemistry, and so you had quantum mechanics, and you had fluid mechanics, and you could think about what happened in a small test tube when molecules came together. But the idea of building something that would make a vast amount of chlorine or plastics or all the things that we use in our daily lives, there was not a field that could do that. And eventually it emerged, and it's called chemical engineering. Okay, and it has its own mathematics. There's new thermodynamics, and out equilibrium thermodynamics is done in chemical engineering more than in chemistry. All right, if you go back 50 years before that, you have electrical engineering. All right, before that, there was Maxwell's equations. So we knew everything about the electromagnetic phenomenon. But it was not clear how to take that and to bring electricity into a home without burning it down, or to build a circuit, or to put communication over the waves given by Maxwell's equations. That was all happened around 50 years, around 1900, and it became called electrical engineering, and it has its own mathematics, a lot of Fourier analysis and so on. And you keep going back to civil and mechanical and all. Each one of these took an existing scientific field and added to it in conceptually interesting ways. This was not just applications of Newton's law or thermodynamics or Maxwell. It was brand new thinking. All right, so what we have now, in my view, in this era, is we have information transmission, we have data, we have statistics and probability and decisions and so on. We have proto-ideas, but we don't have something like Maxwell's equations or the Schrödinger equation. All right, we have a much rougher idea. And we're building these huge factories, these systems that are changing our lives. Okay, so you can say that's just good, that's what humanity should do, it should try crazy things and see if they work. Or you can say, I'm worried about that. I want to make sure there's an actual mathematical understanding of these, like there was for chemical engineering, electrical engineering. It ended up helping society hugely, and eventually there was a solid foundation for it. You know, all of those previous eras led to mathematicians getting involved. You know, Gauss and von Neumann and Kolmogorov all got involved in the era of what was happening in their era. And so I want to encourage you to, if you're interested in some of these things, there is a lot of mathematics. I've been at pains to try to emphasize that. But most of the new ideas are not yet available. We don't know what they're going to be. And so some mathematical thinking will help greatly. Thank you very much.
So now we have a Q&A time. So any question or comment? Yeah, please.
So this is a bit of a meta question.
That's good.
So there's been a debate currently whether or not we're over-investing in LLM or development of LLM. And you pointed out that there are a lot of holes in this program. I wonder if you can actually apply your idea. I mean, when you have a debate, by definition, there's uncertainty. I wonder if you can apply your idea to actually like tell the market, you know, we're doing too much, we're pumping too much money in this aspect of LLM or that aspect of LLM because we don't have enough information yet. Why not spend the money to get the information? I wonder.
No, that's a great question. How do you predict a bubble? And how do you regulate so that you don't have the bubble? You know, so yes, those are questions that, again, economists talk about a lot, but often they don't have the data analysis tools to actually do it. So really what you do have is a decision problem here, bubble or not bubble, and when do you make that decision? All right, and so in some sense, I think these martingale-based tools are the right way to think about it. They are sequential, accrue evidence, and change your mind. And at some point, you can say, I only had 10 data points, and I got a result, but the result is not very convincing. If I got some more data, it would be more convincing. In classical statistics, you're not allowed to do that. That's called p-hacking, okay? You kept going until you got the answer you wanted. In this technology, with martingales, it's allowed. And roughly speaking, you have less power. If you decide after 10 data points, I will make my decision and not change my mind, then you have a lot of power to detect. Here, you have a little less power, but it opens up the possibility of spending more budget for errors later on. And so this is an optimal way to do that kind of decision making. So I do think that this style of thinking is the right one because it allows economics and statistics to come together. Now, as whether or not we're in a bubble, that's my personal opinion. Yes, unquestionably. LLMs are predicting the next word in a sentence. And if you have vast numbers of sentences, they do it pretty well. And they still make some stupid errors, right? And if you do it with mathematics, they will make some stupid errors. Does that mean that they're bad? No, it means they're a useful tool, right? But there's not a clear business model. There's not a clear advantage to humanity for the current LLMs. Eventually they'll be found, but we're spending so much of our energy and young people's minds and money on one thing, and we're not thinking about it in the right way. What is the goal of an LM? To predict the next word or to beat humans? And the problem is that all of the venture capital and the Silicon Valley people think the goal is to build a superhuman. For some reason, it's a Frankenstein-like idea. And that has led to a bubble because the journalists love it and the investors love it, and there's this big bubble. So I would not invest in those companies at all. But as usual, some of them will survive and a lot of them will fall down. There will be a bit of a crisis, and the technology itself will be a part of what comes forward in the future. What I want to kind of look at is what should we aim for in the future, and not just predict the next word in a sentence. Yeah, no, there's, yeah, please, go ahead.
Hi. I have a question. So in news, some mathematicians like Lawrence Tao and Ken Ono start to use LLM to help to do math studies.
Yeah.
But I talk to lots of mathematicians. They don't believe LLM can help a lot in math. What's your view on this?
Yeah, I mean, I have a lot of friends who have a lot of opinions about that. I mean, Terry Tao thinks it can help. You know, he's a convincing person. I think that we're just seeing a sliver right now. We've seen a few months of work on this. In 10 years, it will not replace mathematicians in general, for sure, no question. Will it be a tool that aids lots of mathematicians to go faster? Yeah, because it can try ideas you didn't think about and kind of give you a hint that over there might be something good and not over here. Now, your human intuition is probably better than an LM, and it will be for a long time. But some of those hints that here's a stupid path could save you a lot of time. Okay? And also, there's lots of things in mathematics where there's kind of a standard approach to getting the result. You know, if you solve, you know, you do some mean field approximation, or if you, some quenched, approximation, that you'll get a certain answer. You just don't know how the details will work out and how the expansions will, be controlled and all that stuff. You could think an LM would do a lot of that for you. It's like a smart assistant. It'll just do that. And then you can get your work done faster. But you'll have to be very skilled at using the LM because it'll make some errors and all that. So I think it's clearly a tool going forward, but it'll make mathematics different. And the young people will probably appreciate that. I don't see that problematically. But no, it's not gonna put mathematicians out of business. It will put other people in other fields out of business. And that's, of course, the labor market issues are huge here. Lots of fields that are pretty simple uses of our brains, the LM will do as well or better at half the cost. That's gonna be a big issue for society going forward. I don't know if any other one, this is a debate. It's not a closed question, but I have a student at OpenAI who has worked on the mathematics, and it is. You can take a college advanced real analysis course and take the problems off of it. It will scan those, it will solve them and give you the answers. And that's not, I would have not thought that possible 5 years ago. Now that's old mathematics, it's not at the cutting edge, but it's not clear where that boundary will be.
Okay.
Thank you.
Other more questions or comments? So yeah, for the non-convex optimization problem, sometimes we formulate a primal problem to the dual problem or primal dual.
Yeah.
So you think which one sometimes?
Oh, I almost always do my work with duals.
Oh, with
Almost
dual?
always with conjugate duals. That's kind of our main tool. As you, I'm sure know, the primal problem is not as well regulated as the dual. The dual has nicer properties, especially for designing algorithms that take advantage of smoothness and so on and so forth. And what we were able to prove in that previous work is there's a symplectic interpretation of dual problems for non-convex optimization that leads you to be able to use symplectic integration ideas for those.
To solve it.
Yep,
yep,
that's right.
Yeah.
No, in fact, when you talk about the algorithms behind machine learning, it really is all optimization based, and it's almost always primal dual and all stochastic versions of it. You can never get the real operator. You get a stochastic estimate of the operator, and you prove that still is going to work. And so it's been a very, very productive 10 years in that field. I could have talked about that, but I decided to give a different talk.
So yeah, okay. So then we thank Professor Jordan for his inspiring lecture. Again.
Thank you.
Yeah.